While our focus in subsequent chapters centers on the role that electrons play in atoms and in chemical bonding, for now we're going to turn our attention to the nucleus of the atom. Specifically, we're going to explore radioactivity, a topic of great importance to human health and modern medicine. We've now seen that isotopes of the same element differ only in the number of neutrons present in their nuclei. However, while it's been found that some combinations of neutrons and protons in the nucleus are stable and do not change spontaneously, others are not so stable. In fact, these unstable nuclei emit radiation. Nuclei that emit radiation are said to be radioactive nuclei. Isotopes of elements that emit nuclear radiation are called radioisotopes. In 1896, Henri Becquerel, a French physicist, discovered radioactivity by chance when observing that radiation is emitted from any compound of uranium. Later studies by other investigators showed that the radiation emitted by uranium and by other radioactive elements discovered later can be separated into three types by an electrical or magnetic field. The three types have different electrical charges. One is positive, one is negative, and one carries no charge. The types of radiation were given the names that are still used today. Alpha rays, which are positive, beta rays, which are negative, and gamma rays, which remain uncharged. Today, it is known that other types of particles, such as neutrons and positrons, are also emitted by radioactive nuclei. However, alpha, beta, and gamma rays are still the most common. The table shown here summarizes the characteristics of these forms. In this class, we usually use the symbol given first for each form. The symbols in parentheses are alternatives you might find elsewhere. Except for the high-energy gamma radiation, the radiation emitted by radioactive nuclei consists of streams of particles. The emission of radiation by unstable nuclei is often referred to as radioactive decay. Now, like we saw in Table 2.2 in the previous slide, the particles that make up alpha rays are identical to the nucleus of a helium atom. That is, they are clusters containing 2 protons and 2 neutrons. They have a charge of +2 from the 2 protons. Alpha particles are the most massive particles emitted by radioactive materials, and they have the highest charge of +2. Because of their mass and charge, they collide often with the molecules of any matter through which they travel. As a result of these collisions, their energy is quickly dissipated and they don't travel far. They can't even penetrate through a few sheets of writing paper or the outer cells of our skin. However, exposure to intense alpha radiation can result in severe burns. Despite its side effects, radiation therapy is commonly used in treating various types of cancers. Beta particles are actually electrons, but they are produced within the nucleus and then emitted. They are not part of the group of electrons moving around the nucleus that is responsible for the chemical characteristics of an atom. Beta particles have a charge of -1 and are 7,000 times less massive than alpha particles, so much smaller. They undergo far fewer collisions with the molecules of matter through which they pass, so they are much more penetrating than alpha particles. And finally, gamma rays are not streams of particles, but rays of electromagnetic radiation, just like X-rays. Gamma rays, though, have higher energy than X-rays. Like X-rays, gamma radiation is very penetrating and is dangerous to living organisms. Adequate shielding from gamma rays is provided only by thick layers of heavy materials like metallic lead or concrete. The transformation of one or more atomic nuclei into one or more new nuclei is called a nuclear reaction. The reactants are the substance that undergo the change. By convention, the reactants are written on the left side of the reaction, which can also be referred to as the equation, so you could call it the equation or the reaction. The products are the substances that are formed by the change, and they are written on the right side of the reaction or equation. The reactants and products are separated by an arrow that points from the reactants to the products. A plus sign is used to separate individual reactants or products. So we could have something like A plus B, and then we draw a reaction arrow, and then C. So A and B would be the reactants, and in this case, C would be the product. A nuclear equation is balanced when the sum of the atomic numbers on the left side equals the sum of the atomic numbers on the right side, and the sum of the mass numbers on the left is equal to the sum of the mass numbers on the right. So if you can add and subtract, you can balance a nuclear equation. So we focus on the mass numbers and the atomic numbers in nuclear reactions. Because gamma rays have no mass or atomic numbers, they don't enter into the balancing process of nuclear reactions. However, they do represent energy and should be included in the balanced equations when they are known to be emitted. Although beta particles are electrons ejected from the nucleus of a radioactive atom, we know from our discussions of atomic theory that atomic nuclei contain only protons and neutrons. Where then do the beta particles originate? According to a simplified theory of nuclear behavior, a beta particle or electron is produced in the nucleus when a neutron changes into a proton. And so the balanced equation for the nuclear reaction where a neutron is converted into a proton would look something like this, where we have our neutron, which has a mass of 1, gets converted into a proton, and then we have our beta particle, which is 0 and -1, like this. So you can see that the sum of 1 and -1 equals 0, and you can also see that the sum of 1 and 0 equals 1. So our mass numbers are the same when we tally them up on both sides, and our atomic numbers are the same on both sides when we tally them up. So you notice the criteria for balancing this equation are satisfied. Again, the mass numbers balance out. 1 is equal to 1 plus 0, and the atomic numbers balance out. 0 is equal to 1 plus -1. Thus, a nuclear neutron is converted into a proton during beta emission. So again, we gave off a beta particle, and you can see our neutron was converted into a proton in the process. And so the daughter nucleus, what's formed as a product, has an atomic number that's higher by 1 than the decaying nucleus. Similar changes in nuclear particles occur when nuclei decay by positron emission. A positron is a positively charged electron. When a nucleus emits a positron, the nuclear proton is changed into a neutron, so the daughter nucleus has an atomic number that's lower by 1 than the decaying nucleus. Positron-emitting isotopes are used in diagnostic positron emission tomography, PET scans of the brain. Certain nuclear changes occur when an electron from outside the nucleus is drawn into the nucleus, where it converts a proton into a neutron. This process is called electron capture and is not as common as the beta decay or the alpha decay or something like that. The daughter nucleus in electron capture has an atomic number that's 1 less than the decaying nucleus. Okay, so that seemed like a lot of intimidating information maybe, but let me show you how to solve a problem balancing a nuclear equation, and you'll be able to do it very quickly. So it says here, americium-241 nuclei undergo radioactive decay by emitting an alpha particle and changing into the nucleus of another element. So we have americium-241 that emits an alpha particle and then it becomes another element. So write appropriate symbols for americium-241. So let's start with that. So first we need to find americium in the periodic table. And I'm not going to go over to the periodic table right now, but americium is element number 95. So we're going to put down here 95 AM, right? So this is our atomic number, and then our mass number it's telling us is 241. So we have americium-241. Then we're going to emit a beta particle, an alpha particle. So if we go back to the alpha particle, so I'm going to scroll here on the slides. So an alpha particle can be written like this with alpha, 4 as the mass number, and 2 is the atomic number. So I'm going to write it that way. So we have our americium-241, which is going to emit our alpha particle like this. Okay, and then it's going to also produce some kind of other nucleus. Okay, so what is the other nucleus or the other atom that's going to be formed? So remember, the atomic numbers have to add up. So 95 is going to be equal to 2 plus something. Well, 2 plus what gives me 95? The answer is 93. So what element is element number 93? Go to your periodic table and you'll see it's neptunium. Well, what's the mass number of our neptunium? Well, I told you that, remember, the mass numbers have to add up as well. So 241 is going to be equal to 4 plus something. Now, what plus 241 What plus 4 is equal to 241? And the answer is 237. Sorry about that. So the answer is Neptunium-237. And there's your balanced equation. So again, and I'm repeating myself, okay, you see that the atomic numbers balance out, okay, 2 plus 93 is equal to 95. And you see that the mass numbers balance out, right? 237 plus 4 is equal to 241. And that is how you balance a nuclear equation. There's nothing more to it than that. You should go into the textbook and practice the other ones with beta particles and positrons as well. But again, it's the same thing every time. This slide just shows you, information about the positron and electron capture, which I already discussed on a previous slide. You should just memorize that a positron has a mass number of 1 and an atomic number of 0. Some radioactive isotopes are more stable than others. The more stable isotopes undergo radioactive decay more slowly than the less stable isotopes. The half-life of an isotope is used to indicate its stability, and it is equal to the time required for 1/2 of the atoms of a sample of the isotope to decay. So table 2.3 shown here lists isotopes with a wide range of half-lives. And so if we look at something like carbon, so let me get my red pen out here. So if you look at carbon, it has a half-life of 5,600 years. Then you look at something like oxygen-16, which has a half-life of 2 minutes. And then you have something like, wow, uranium-238, 4.5 times 10 to the power of 9. We'll just say that's a long, long time. Okay, very long half-life. So the fraction of the original radioactive atoms remaining in a sample after a specific time has passed can be determined from the half-life. After one half-life has passed, half of the original number have decayed, so half remain. During the next half-life, half of the remaining 1/2 decay, so 1/4 of the original atoms remain. And after 3 half-lives, it would be 1/2 times 1/2 times 1/2, which would give you 1/8 of the original atoms remaining undecayed. The fraction of original radioactive atoms remaining in a sample after a specific time has passed can be determined from the half-life. After one half-life has passed, half of the original number have decayed, so 1/2 remain. During the second half-life, half of the original, during the second half-life, half of the remaining 1/2 decay, so you're left over with 1/4. And after 3 half-lives, it would be 1/2 times 1/2 times 1/2, which would give you 1/8 of the original atoms remain undecayed. Okay, let's try a question. It says the activity, amount of radiation emitted of a radioactive substance is measured at 9 a.m. and 5 p.m. The activity is found to be 1/16 of the original 9 a.m. value. So what's the half-life of the radioactive material? Well, to get to 1/16, you'd have to take 1/2 times 1/2 times 1/2 times 1/2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So that would give you 1/16. So that means it's 4 half-lives. Okay? So if we go from 9 a.m. to 5 p.m., that's a total of 8 hours. So if we take 8 hours and we divide by 4, I'll just put t 1/2 like this. That gives you 2 hours per half-life. So each half-life is 2 hours. The amount of radiation given off by a sample of radioactive material is proportional to the number of radioactive atoms present in the sample. The amount of radiation given off is called the activity of the sample and is measured by various instruments of detection. Radiation can be described in either physical or biological units. Physical units of radiation indicate the activity of a source of radiation, while biological units are related to the damage caused by the radiation. Physical units include the becquerel, named after Henri Becquerel, and the curie, named after the Polish-French chemist and physicist Marie Curie. Biological units account for the fact that a given quantity of a type of radiation doesn't have the same effect on tissue as a given quantity of another type of radiation. Rad and Gray describe the amount of energy transferred from the radiation to the tissue which it passes. Lastly, the sievert and the REM are biological units devised to account for differences that various types of radiation have on health. The advantage of the REM, the REM, is that individuals exposed to low levels of various types of radiation have to keep track only of the REMs absorbed from each type of radiation and add them up to get the total health effect. The presence of radiation can be detected in several ways. A Geiger-Müller tube, or a Geiger counter, measures radiation as it passes between charged electrodes in the presence of a low-pressure gas. These instruments are very useful for detecting radiation in a variety of environments, but can't distinguish between types of radiation. They also have difficulty retaining accuracy at high levels of exposure. A scintillation counter measures flashes when radiation reacts with certain substances to emit visible light. Many workers in medical settings use simple film badges to track exposure to radiation over time. Radiation can be hazardous to living organisms, but do we know why? What does radiation do that's so dangerous? The greatest danger to living organisms results from the ability of high-energy or ionizing radiation to knock electrons out of compounds and generate particles called radicals or free radicals in the tissue through which the radiation passes. These electron-deficient particles are very reactive. They cause reactions to occur among more stable materials in the cells of living organisms. When these reactions involve genetic materials like genes or chromosomes, the changes might lead to genetic mutations, cancer, or other serious consequences. Long-term exposure to low-level radiation is more likely to cause these kinds of problems than short exposures to intense radiation. Short-term intense radiation tends to destroy tissue rapidly in the area exposed and can cause symptoms of so-called acute radiation syndrome. Some of these symptoms are listed in Table 2.5 in the textbook. The rapid destruction of tissue makes relatively intense radiation a useful tool in the treatment of some cancers. And you can see that in the table, it goes all the way from 0 to 25, which has no detectable clinical effects, to 20 to 100 rems, where you have a slight or short-term reduction in number of some blood cells, okay? But then you go up to a high level, like 600 or more, which can have really bad side effects, and, it can even kill you, okay? So you got to be very careful with radiation exposure. And so, yes, radiation is dangerous, but if you use the radiation and target, certain cells that might be metastasizing in something like cancer, it's going to destroy those cells, which are more rapidly producing than healthy cells. But if you think about, okay, well, what are some of the cells that reproduce the most quickly in a person? It would be something like your hair follicles, right? Those cells regenerate very quickly, and that's why when people are undergoing radiation therapy, they'll oftentimes lose their hair because it's going to attack those cells as well, because they undergo mitosis so quickly. The health hazards presented by radiation make it imperative to minimize exposures. This is especially true for individuals with occupations that continually present opportunities for exposure. Like your dentist, when they take an x-ray of your teeth, what do? They go and hide behind the door or something, right? So one approach is to absorb radiation by shielding. As shown here in Table 2.6, alpha and beta rays are easiest to stop. Gamma radiation and X-rays require the use of very dense materials like lead to provide protection. If the type of radiation is known, a careful choice of shielding materials can provide effective protection. Another protection against radiation is distance. Because radiation spreads in all directions from a source, the amount falling on a given area decreases the farther that area is from the source. If you double the distance from the source, then the amount of radiation that reaches the area is only 1/4 of what it was before. Radioisotopes undergo the same chemical reactions as non-radioactive isotopes of the same element. This characteristic, together with the fact that the location of radioisotopes in the body can be readily detected, makes them useful for diagnostic and therapeutic medical applications. In diagnostic applications, radioisotopes are used as tracers whose progress through the body or localization in specific organs can be followed. To minimize the risks to patients from exposure to radiation, radioisotopes used as diagnostic tracers should have as many of the following characteristics as possible. Number 1, tracers should have a short half-life so that they will decay while the diagnosis is being done, but will give off as little radiation as possible after the diagnostic procedure is completed. Number 2, the daughter nuclei produced by the decaying radioisotope should be non-toxic and give off little or no radiation on their own. Ideally, they would be stable. Number 3, the radioisotope should have a long enough half-life to allow it to be prepared and administered conveniently. 4, the radiation given off by the radioisotope should be penetrating gamma rays, if possible, to ensure that they can be detected readily by detectors located outside the body. The radioisotope should have the chemical properties that make it possible for the tissue to be studied to either concentrate it in diseased areas and form a hotspot, or essentially reject it from the diseased areas and form a cold spot. The thyroid gland concentrates iodine and uses it in the production of thyroxine, an iodine-containing hormone. Iodine is an excellent diagnostic tracer for determining whether the thyroid gland is functioning properly because the thyroid is the only tissue in the body that uses iodine. Iodine-123 is a good tracer because it is a gamma emitter with a half-life of 13 hours. Iodine-131 is also radioactive and has a short half-life of 8 days, but it emits gamma and beta radiation. Beta radiation cannot penetrate the tissue to be detected diagnostically and therefore is simply an added radiation risk to the patient. For this reason, iodine-123 is preferred. An overactive thyroid absorbs more iodine and forms a hotspot, whereas an underactive or non-active gland absorbs less iodine and may show a cold spot on a thyroid scan, like you see here. Radioisotopes administered internally for therapeutic use should ideally have the following characteristics. 1. The radioisotope should be an alpha or beta emitter because radiation in these forms is less penetrating through tissue than gamma emitters and thus restricts the extent of damage to the desired tissue. 2. The half-life should be long enough to allow sufficient time for the desired therapy to be accomplished. 3. The decay products should be non-toxic and give off little or no radiation. 4. The target tissue should concentrate the radioisotope so that the radiation damage is restricted to the target tissue. Iodine-131, for example, is used therapeutically to treat thyroid cancer and hyperthyroidism. Its primary advantage is the ability of the thyroid tissue to absorb it and localize its effects. Until the mid-1950s, when improvements in the generation of penetrating X-rays made them the therapy of choice, cobalt-60 was widely used to treat cancer. Cobalt-60 emits a beta and gamma radiation and has a half-life of 5.3 years. When used therapeutically today, a sample of cobalt-60 is placed in a heavy lead container with a window aimed at the cancerous site. The beam of gamma radiation that exits through the window is focused on a small area of the body where the tumor is located. Table 2.7 lists some other examples of radioisotopes used diagnostically and therapeutically.